Hey everyone, I'm joined today by Wilson Lin from Cursor, who made headlines recently for building an entire browser that can render web pages as a solo project with the assistance of vast numbers of coding agents. And yeah, Wilson, I'd love to hear more about how you came to this project and how this fits into the work that you do at Cursor.
Yeah, of course. So just by introduction, hey Ron, my name is Wilson. I'm a product engineer at Cursor. This project is a research project we have to experiment with how to scale out coding agents beyond a single agent and observe their behaviors, see how we can get high throughput and perhaps investigate some of the issues that may arise from many agents collaborating, such as like synchronization overhead, communication, that kind of stuff. Yeah. So FastRender was a personal project of mine from, let's say, November. It was an experiment of mine to see how well front-end models like Opus 4.5 and back then GPT 5.1 could do with much more complex, difficult tasks. And in my mind, I thought, a browser rendering engine is very complex and something that I have, personal interest in. Initially, the scope was even smaller. It was just, can you render a screenshot of web pages, like a URL, and doesn't need to have JavaScript or anything, but there was sufficient complexity from just, understanding spec, CSS, HTML, implementing most of the CSS features, laying out things in a reasonably accurate way, and handling the kind of diversity of the web. And that's kind of how the FastRender project started. As that experiment progressed, I was seeing, better and better results from single agents that were able to actually make good progress on this project. And at that point, I wanted to see, well, what's the next level? How do I push this even further? And in my mind, it was.
I feel like this mirrors a lot of people spent the holidays, like December, poking at the edge of these brand new models, because Opus 4.5 came out in November, GPT 5.2 was December.
That's
and
right.
we were all poking at them, and I know I was trying difficult things and it would do them. I think, okay, what's more difficult? And just keeping on stepping up the challenge of what you're throwing at these things. And it's kind of fascinating how well they can crunch through. But yeah, I've been basically stuck in single agent land. The idea of pushing it out to multiple agents to take on something this ambitious is very exciting to me.
Yeah, I totally agree. And my project or experiment of the week over the break was to, take these highly intelligent agents and then try to linearly scale them, get more throughput, because browser engine is sufficiently complex and is sufficiently, parallel work that can be done to the various subsystems that it seemed like this was possible. And that's how the experiment started, research.
And let's see where you've got now. So we're looking at FastRender right now. So FastRender is this window here. It's displaying its own README on GitHub, which, given how complex GitHub has got over the past few years, I think this is a pretty good starting point. But what kind of things can it do? What sort of web pages is FastRender capable of rendering?
Yeah, for now, definitely more towards the simple and basic text-oriented pages. So, for example, going to Wikipedia, it loads pretty fast and renders pretty accurately, although obviously lots of subtle layout issues and stuff.
Well, I noticed the sidebar there, that appearance sidebar, that looks to me like something which might be a JavaScript feature, but JavaScript isn't running.
Yeah, that's right. So JavaScript is disabled right now, which the agents made that decision as it was currently still implementing out the engine and likely to get make progress towards other parts of the engine. Is decided to turn that off or put it behind a feature flag, technically.
Feature flag.
Yeah, that's right.
I love that your agents are now deciding on their own feature flag. That's pretty amazing. But so this is Wikipedia, and we've seen GitHub. Can we pull up a CNN.com or something like that?
Sure. Yeah, CNN is a bit more complex page. There's a lot of content and images, so this will likely take a little longer to render. Let's take a look how it goes.
Yeah, breaking news and video. You don't have video implemented just yet, do you?
That's right. No.
But that's considering how heavy that site is. That's a a pretty decent starting point.
Yes.
So you mentioned that you started out building things with, it was effectively the sort of Claude Code model, or just trying out different coding agents and churning away. How did you get from that to running multiple agents at once? And what's your peak agent? Like how many of these things do you have running at any one time at the highest point?
Yeah, so at the peak, when we had the stable system running for 1 week continuously, there were approximately 2,000 agents running concurrently at one time, and they were making, I believe, thousands of commits per hour. Yeah.
I mean, I saw your GitHub repository has 30,000 commits now, so that's
right.
enormous quantity of enormous amount of activity going on there. How do you run 2,000, 20,000 agents in one time? Are they all running in different environments?
That's right. So, the simple approach we took with the infrastructure was to have a large machine run one of these multi-agent harnesses. So each machine had ample resources, and it would run about 300 agents concurrently on each. And this was able to scale and run reasonably well, as agents spend a lot of time thinking and not just running tools. And system was not like too overloaded, and it was a simple way to kind of.
Can you show us what that looks like when it's running?
Sure, I can give you a quick demo of the internal terminal UI we have for one of these. So this is one of the machines that is running one of this multi-agent harness and this custom TUI for our custom harness. And you can see the kind of activity that's going on, the continuous stream of tool calls that's happening, and the set of agents, which there are many more that you can't see on the screen yet, but or have already completed, that are operating under this one instruction or initial prompt. Yeah.
And so this right here is that what's the sort of overall task that this cluster of agents is working towards?
So this cluster of agents is working towards building out the CSS aspects of the browser, whether that's like parsing. You can see some of the other aspects like selector engine, those features. And this is actually because we managed to push this even further by splitting out the browser project into multiple instructions or work streams, and have each one run one of these harnesses on their own machine. So that was able to further parallelize and increase throughput. Yeah.
So this is effectively the same challenge as running a giant engineering team split into modules that are handling different aspects of the implementation.
That's right. Yeah. And you can imagine why we needed a very large machine, because it's like having 100 or 200 engineers working and compiling a browser on the same machine. So
are the agents constantly dealing with merge conflicts? Like, how do they get their commits in a way that doesn't overlap each other?
Yeah, that's a very good question. So we've noticed that most commits do not have merge conflicts. And the reason is the harness itself, which I can go into more detail, is able to quite effectively split out and divide the scope and tasks such that it tries to minimize the amount of like overlap of work. And that's also reflected in the code structure. And so it tends to be that commits will be made at various times, and they don't tend to touch each other at the same time. Now, it does happen, and there's mechanisms and prompts within the system to get agents to handle those, resolve conflicts without just merely overwriting. But it's a reasonably minimal rate, and that is like one of the aspects of this research, which is how do you minimize these kind of things that could become bottlenecks and prevent the kind of scalability of such a system.
So it mainly comes down to the planning, right? It's how good is the sort of top level agent at planning out the work such that it can be worked on independently.
That's right. And our approach for this, which I can go into to do that, was we have the concept of planners and workers, as you can see here. And planners are the ones who are responsible for delivering and owning a specific slice of the instruction or work, and they are able to delegate that to subplanners. for example, the scope is very large. And so the behavior, the emergent behavior from the system tends to be quite effectively cleanly divided ownership and scope. So so the root agent is responsible for delivering all the work and all the scope, the project, for example, but it can divide into, we can delegate and divide a specific feature or specific subset of the task to this planet agent. And that planet agent cannot, via prompting, is instructed not to try to, exceed the scope. And we found that to work quite well for effectively dividing.
How long have you spent iterating on the sort of prompts that drive the planning? Like, how much of the work that you've been doing has been around that sort of meta level of figuring out how to prompt them such that they can split the work up?
Yes. So the harness itself, this experiment harness, definitely was a lot of work to experiment, to iterate on prompting, as well as the system. And it kind of evolved over the period of 3 weeks to see not only the subtle tweaks to the prompting, but like what is the actual ideal architecture? Because there were actually previous architectures we tried that turned out to be quite bad at linearly scaling agents, and we took lessons from those and came up with this kind of final design that has kind of worked pretty well for us and ran continuously for long periods of times. Yeah.
And so, how much of your sort of mental effort is around understanding browser rendering and how a browser should be built and what all the components are, versus how much the time that you're spent thinking about agent coordination and having the agents do the rendering, planning, and so forth?
Yeah. So definitely I would say the browser and this project were kind of co-developed and very symbiotic, only because the browser was a very useful objective for us to measure and iterate the progress of the harness. But the goal was to iterate on and research the multi-agent harness, and not the browser was just a kind of research example or objective.
Okay.
Example objective. I would say that definitely the instructions that you feed into this harness is very important. And so there is that aspect of like, in some sense, the effectiveness of this system depends on how rigorous, how well specified, how correct your initial instructions are. Because, for example, there were actually a lot of encoded decisions that I made that were not ideal for the goal I was trying to achieve, because I did not have as much experience building a browser, let's say. And the agent worked effectively, but it was working effectively towards a prompt. It was like obeying the prompt very rigorously. And so it would, implement out some decisions that were not ideal. But that in some sense, that's like separate from.
I guess that's the joy of building a browser is literally the 3 words: build a browser, encode a million requirements already. Like, it's pretty well established within training data and specifications and so forth what a browser is. So it's like the smallest description of a project can turn into the most amount of work almost. So I noticed that in your repository, you've got a bunch of Git submodules that pull in specifications for CSS and HTML and so forth. How important has that been? Like, how much of the agents referring to those specifications in the work that they're doing?
Yeah, it has been very important. I think we'll have more, technical write-up and reports on the research results later. But it's feedback loops to the system is very important. Agents are working, as you can see, for very long periods continuously, and without the kind of guardrails and feedback mechanisms to know whether what it's doing is right or wrong, can have a big impact on over a long period, long rollout. So specs are definitely an important part. You can see lots of comments in the codebase that AI wrote, referring specifically to specs that are found in the specs submodules. You can see, whether it's like high level or low level. There's also like other feedback mechanisms. For example, it used some of the WPT test examples to make sure that it's spec compliant.
Platform tests, right? That which are independent from the specifications, but help prove that they're all working.
That's right.
I remember years ago, ACID 3 was the sort of
That's
killer.
right.
But that was about 15 years ago now. So
yeah,
presumably all sorts of modern alternatives to that.
Yeah, and I think I think also you can see it in a way that without the ability to have feedback mechanisms, it does actually tend to not write as good code. Like it tends to drift to it, just as a normal agent would, because for example, there's some parts of the code base that may be writing macOS code, and that can't be tested on a Linux machine, or can't be compiled, or the language is more dynamic. And of course, you can run that if you had a Mac machine, but also the nice thing about Rust is you can get a lot of verification just from compilation, and that is not as available in other languages. So there's lots of ways in that you can see the impact of having grounding, having feedback loops, having things that kind of keep it aligned and on track.
And on the subject of feedback loops, a browser is an inherently visual problem. Are you using are you feeding screenshots back into the model to help it figure out what's working?
That's right. In the earlier evolution of this project, when it was just doing the static renderings of the screenshots, this was definitely a very explicit thing we told it to do. And these models are visual models, so they do have that ability. We have progress indicators to tell it to compare the diff against a golden sample. Or
are you doing visual diffs between snapshot images?
It was one mechanism it had, and another one would be just manually looking at the screenshot output and seeing And
you say manually, you mean the model itself is manually?
Yes, sorry. The model itself is looking at it's manually grabbing the image and looking at it, and not in some kind of automated.
Which model did you end up settling? Which models are doing most of the work at this point?
Almost all the models were GPT 5.2 or 5.1 before 5.2 was released.
And you found that you're using 5.2 but not 5.2 codecs for this?
That's right. Yes. Some initial findings was that the instructions here were kind of more expansive than merely coding and engineering. For example, how to kind of operate and interact within a harness, or how to kind of operate autonomously and work without interacting with the user or having a lot of user feedback. And these kind of instructions we found did kind of work better with the general models, and I think arguably because they're more able to understand the general instructions. I definitely think there's a lot more we can do to kind of research what's the kind of ideal models here and the kind of effects the model pick has. Yeah.
And then what's the longest you've seen this stuff run complete without any interactions from a human being?
So this system, once you give an instruction, there's actually no way to steer it. You can't prompt it. You can't adjust how it goes. The only thing you can do is stop it. So our longest run, all the runs are basically autonomous. We don't alter the trajectory while they're executing. And so the longest run, well, you can see here we have one running for quite a while now, but the one we did at the time of the post was about a week, and that's pretty close to the longest. Of course, the research project itself was only about 3 weeks, so we probably can go longer. Yeah.
What did FastRender look like at the beginning of the week, and what did it look like at the end of the week? What did the swarm of agents get done in those 7 days?
That's a great question. So we did actually post a time screenshots from various snapshots in history, and you could see how it kind of evolved in its alignment, in its implementation of the engine. It's getting more things correct. It's running more things accurately. I can pull this up for you if you like.
Because I'm thinking, so the guidance for that week really was make it better. If you've got a browser, it's not good enough, do more, right?
Right. That's right. There's guidance around just implementing more of the spec, comparing against some of the, like what you said, the visual diffs, and making sure that kind of integration is working. Performance, that was another important one.
Because your planners, they're arranged effectively in a tree, right? So
That's right.
the root planner at the very bottom, the one that's just like, okay, make the browser better, and then it spins up, okay, you're a planner with a tree rating around performance, and you're one that's rated around CSS improvements and so forth.
Yeah, that's right. So the as you get down the northern leaf nodes, the tasks are more and more specific. The planners are more and more narrow scoped. And the interesting thing is that like all agents, whether workers or planners, when they finish, they actually do send they don't directly send the response to the parent, but they kind of provide a handoff that is the system then provides to the planner that spawned the task. And so the system can actually continue to work and kind of dynamically respond to new information or progress or even regressions and stuff. So there's a lot of like continuous motion that's available.
And so what's the overall sort of scoring function? Like what's the question that the top level planner is answering every now and then, just to make sure that it is getting better and going in the right direction?
For now, they like all the planners, including the root, are primarily focused on obeying instructions. So the metric is really just, did it successfully complete the task that it was instructed to do so. Yeah.
But the top level, it just assumes that it's issued the correct instructions, and that if those instructions are completed, then the job is done, right?
That's right. So it's very much like an agent. Like you give it a prompt, and its goal is to kind of follow the instructions and make sure.
Is your expectation as the sort of ultimate human in the loop that occasionally you'll need to take a look at what's going on and say, you know what, new top level instruction, you need to make sure that, say, Google.com renders correctly. This is your new goal to go after. Is that the sort of level that you're thinking at now?
Yes, in some sense that's correct. You can, for example, you're seeing you have an instruction that's like working on implementing some specs, and you feel like you could continue to parallelize more work, but in a more prioritizing in a different way. For example, like you said, like instead of going deeper on the spec area, you want to focus on getting some pages to render correctly. I would say because these instructions, the system is following your instructions, most of the time, it's really about you're observing that, oh, it's doing something that is correct according to your instructions, but it's something that you didn't actually think about in your instructions. So it's like it's more like you need to clarify your instructions because it's going to rigorously stick to whatever you say.
Okay, so if you were to decide that the next big goal is to be able to is web GPU support or WebAssembly support, what would you do? Like, what actions would you take to get the system to start crunching on that new set of problems?
So I would first draft out a very detailed spec, and not so detailed that you're like dictating how exactly the code should be or the structure, because these are highly intelligent agents that there are planners here that can handle that dynamically and perhaps make some of those decisions at the time of running. But I would definitely lay out exactly what I want to see implemented in terms of features, in terms of like the corner cases, boundaries, deliverables, what to prioritize. And I do find that collaborating with AI on this is quite helpful because they can kind of cover things you overlooked, or they can help you kind of flesh out a bit more detail on some underspecified parts. And then once you have that very detailed instruction, you want it to be detailed because there's so much capability and it's going to run for a long time. You want to make sure it's like really on track, exactly what you want. You then just simply pass it to the system, and it just begins running agents. And,
so if you were going to WebAssembly, would you expect to come up with a specification that would say a few pages of notes and feed those in? Like, how much work would you expect to need to produce in order to get your swarm of thousands of agents tackling a problem of that scale?
That's a very good question, and I think the browser itself perhaps is quite interesting and distinct because there's already a lot of specification out there. So WebAssembly or CSS or HTML is already quite well specified, and so I would perhaps in my plan lay out a lot of detail about how it should be engineered or should be implemented. But I would also probably like we talked about before, we have the specifications inside the repo, and we say you make sure you refer to the specifications.
So I've been building a WebAssembly implementation in pure Python just to play around for exactly the same kind of reasons you're doing here. And yet one of the neat things about the WebAssembly spec is it's got a conformance suite baked into it. There's you check out the spec and it literally comes with a giant ball of test cases that you can set the agent to start churning through. And I found that works incredibly well as a sort of starting point.
Yeah, I agree. I think those kind of comprehensive tests, rigorous tests help a lot. And I think that's one of the benefits of having picked the browser as a project for this for this experiment. Yeah.
Let's look at some code. Let's dive a little bit into the. It's over 1 million lines of Rust at this point. Is that right?
That's right. Yeah.
Wow. Let's because I know I've seen people raise questions online about dependencies. Can we have a poke around in your cargo.toml and see the dependencies that the agents have chosen to use here?
Yes. Let me move this. You can see some of the features it's added.
All right. What are the most in? Ooh, what was that? An MP4? Oh, here we go.
Yes, there's the dependencies. Yeah.
Gotcha. Yeah, and so some of these are kind of you just like base 64, etc. You'd expect. What I saw, I know that there are dependencies in here like skier and half buzz, which are sort of rendering. And were those things that you selected, or those things that the agents found themselves?
The agents made the decision to select those, and I think I think when upon reflection, I think that's something that what you could argue is quite reasonable because whether they're like quite common low-level dependencies that perhaps like other browsers also use.
Yeah, like half-buzz is a text rendering dependency, right? It can
take
fonts and render them on screen, and it would seem like that's an entirely separate project to have your agents go and build their own font rendering from scratch. There are some of these that are a little bit more sort of eyebrow raising, like CSS parser or the markup 5 ever. Is that I think that's an HTML5 parsing library. Is that right?
That's right. Yeah, I agree. Well, similarly, these are dependencies that I think the agent picked to use for small parts of the engine, and it should have actually implemented it itself. And I think this is actually once like kind of a reflection on how the importance of the instructions, because I actually never encoded specifically that like what level of dependencies we should be implementing ourselves, what you should not be pulling in, because those are the kind of things that I overlooked in my instructions.
So that becomes almost like a it's like that the planners themselves have this idea that okay, I'm building out the rendering engine, but they didn't have specifically tight guidelines. But they at the same time they didn't just say okay, well I'm going to clone Firefox and do it that way. I guess partly you're working in Rust here, right? So
right, that's right.
You'd be more likely to, and I know some of the components of the Servo project ended up in here, right?
Yeah, that's right. And after I was realizing this, we've adjusted the instructions to say you should not be using these kind of dependencies. The goal is explicitly spelled out that the goal is to kind of rewrite a lot of the stack or implement itself, because that's the kind of experiment. And perhaps some of that was kind of oversight in the instructions, or they were kind of artifacts from previous evolutions of this project. When it was smaller scoped and it was focused solely on the browser engine, which we kind of quickly scoped, increased the scope. We didn't pull these out. I think also that it did implement a lot of the core significant parts like table layouts, CSS cascade. And as it kind of increases scope, it will probably start to prioritize like bringing these other dependencies in, like bring these the next kind of level of dependencies into the repo.
Gotcha. And so do you have sort of confidence right now that you haven't basically got a 30,000 commit wrapper around the servo rendering library? Like it seems pretty clear from me, having like seen the thing running, that it's not wrapping an existing rendering framework.
That's right. Yeah, there's definitely no just directly importing the servo library or any kind of browser engine. And when you run the browser, you can clearly see that. We've noted some of the servo dependencies it pulled in were like the kind of, like you say here, like the CSS parser, things that it can and should kind of implement itself. But yeah, there's definitely a lot of lines of code that implement a lot of significant parts of the layout engine, and our goal is to try and continue to increase that. We've already started a new run of these with a lot of the dependencies completely in-house and written from scratch. Yeah.
Gotcha. I thought one of the most interesting ones, there's a library called Taffy, which I think is a CSS grids and flexbox layout library. And is that how much of the heavy lifting at the moment is being carried out by that dependency?
So it is currently vended, and as the agents work on it, they do make changes to it. This was actually an artifact from like the very early days of the project before it was a fully fledged browser, and it was kind of left there. It is implementing like a small. It's implementing like the flex and grid layout engines, but there are other layout engines like inline, block, and table.
Right.
This engine is doing, and I think in our new experiment, we're removing that completely, and it's.
You're going to pull Taffy out. Interesting, because it's that's I thought that was a particularly interesting dependency, because it's not actually just used for browsers at all. I've seen Taffy show up in all sorts of other applications as a way of doing these more complicated like rendering operations. And then the last one is JavaScript. So I know you've got two JavaScript engines listed in here at the moment. You've got ECMA-RS, which is yours, and then there's QuickJS that's snuck in there as well. How are those two JavaScript implementations working at the moment?
Yeah, so ECMA-RS was like another project that we ran, AI coding, including this kind of multi-agent system on, and it was writing, most of the kind of a parser and type checker from just using AI. And initially this project didn't have the FastRender project didn't use JavaScript. As we expanded scope to ask for JavaScript, thinking was that if we task it to write a JavaScript engine from scratch, it's kind of already doing that in a separate project, so we can just kind of merge these two together.
So the ECMA-RS is your separate, like from the browser, a JavaScript experiment that you were doing.
Yes, for example, we were running it to experiment to see if we could get to 100% the test 262
Gotcha.
Yeah, and implement a TypeScript compiler in Rust. And similarly, using a lot of the kind of feedback mechanisms like the TypeScript spec and TypeScript testing. And the QuickJS is a dependency that was pulled in by an agent to a specific small kind of project code gen, which I for the web IDO, and it was not like part of the main engine. The main browser engine is using the.
What an interesting decision! I'd have expected it to run Node.js or Dino or something.
Yes,
but did it pull it in QuickJS, which is a C library, and actually like hook that up to the Rust code, or was it running it completely independently?
It was using the Rust library of QuickJS.
Right. So. That's so interesting, because I guess when you've got such a complex tree of agents, any one of them could decide, you know what, I need to pull in QuickJS to run this piece of code here, to run this, to generate that, and that's fascinating. It feels like one of the challenges here is sort of an observability challenge. With all of these things going on, you need mechanisms you can use to keep track of the individual decisions that they're all making.
For sure. I think observability, something that we're like actually researching as part of this. It's a very much interesting area of research. How do you kind of get a very high-level assurance, no view of what's going on in the system, perhaps ability to, in fact, like stare at while it is executing. Just for an interesting thing about that decision, though, because a lot of these decisions are made by these agents by themselves. I believe it mentioned that it pulled in the QuickJS because it knew that other agents were working on the JavaScript engine, and it needed to unblock itself quickly to do the code.
Oh, that's hilarious.
So,
Did it actually said that? Well, I'm gonna have to pull in this because those slackers haven't got my job.
And it was like eventually once that's finished, let's remove it and replace it with the proper engine. So I thought that was quite fascinating. Yeah, there's a lot of fascinating.
Weird how close.
How
a team of human engineers would work. That's so interesting. So let's finish by talking about like future. So firstly, it feels to me like the real secret sauce behind all of this is the harness that you've been building that lets you find these things out. Is that still purely a research project, or is that something that you might become like open source or part of Cursor in the future?
At this point, it's definitely an open research project. There's a lot of really interesting questions here. I think a lot of questions around like how do you ensure you can get the throughput and scalability of such system, but with the rest of the software development lifecycle. How do you do things like reviewing code or ensuring kind of correctness? Do we need kind of new primitives to new environments for these long-running autonomous agents? And there are questions around like the observability and the steerability we discussed. And I think there's a lot of interesting questions like just about capability in general. I think it was surprising to us that like, definitely far from a production system and, not 100% correct or optimal code, but, the fact that a few 100 or 1,000 agents concurrently can actually work together and produce code that is like 99% compilable and runs and is mostly aligned to the way you instructed it was kind of a very interesting result that we found. And
for me, the biggest story here is that a single engineer over the course of 4 weeks, when armed with this stuff, can produce over 1 million lines of Rust code that mostly works, right?
That's right. Yeah.
A very, very challenging goal, and then can continue to iterate on that and redirect it and so forth. I think this is such a fascinating example of the ultimate extremes of what's possible in January of 2026 using this set of tools. And then FastRender itself, what are your future plans for the browser project? Like at what point do you draw a line under it and say, you know what, we've learned all that we can. This is as far as we're going to go.
Yeah, I think there is still some, even currently right now, some continued experiments around, for example, what we learned about dependencies that we mentioned, things about like, well, could the agents work much faster and even more effectively if we had like spent some time to reorganize the structure and the project to be more aligned to the project, because as I mentioned, this is kind of a evolution from a small static renderer project. And for example, this project is right now a very large monolith, and there's actually in some ways it slows down the system because the agents have to spend a lot of time waiting for code to compile to test every single change, and that actually has an impact on the throughput, even though it has it's nothing to do with the harness itself. So there's a lot of interesting experiments there. I think
this is the microservices thing, right? The companies that did well with microservices, eventually, microservices are always an organizational hack. It's like, how can we just break the code base up so that our teams in different places can work more productively individually? And now you're having to say the same things, but for like, what's the browser equivalent of a microservice structure so that your 2,000 agents can work more effectively at the same time? That's so interesting.
Well, there's something interesting like related there too, which is we definitely wanted to optimize for throughput, right? Because as we say, like if in theory you may have like 100 agents, but if in reality there's bottlenecks, it's not really going to be scaled linearly. And so one of the trade-offs was, well, if you wanted every single commit to be 100% perfect, make sure it can always compile every time, that might be a kind of synchronization bottleneck. And what's interesting is that you can actually see, especially as you break up the system into these kind of more modularized aspects, you can see that errors kind of get introduced, but small errors, right? Like because like API change or just some syntax error, but then they kind of get fixed really quickly after a few commits. But then some new issue maybe arise, and then it gets fixed. So there's this kind of like a little bit of slack in the system to allow these kind of temporary errors, so that the overall system can continue to make progress really at a really high throughput.
Wow.
Because if you required every single commit to say pass 100%, you suddenly have like, oh, now I have to my agent has to fix some other part of the code base and make sure that can pile before I pass.
Again, all of this stuff maps back to large-scale software engineering with teams.
Right, exactly.
Just that now you've got programmers that will churn out 100 lines of code in a minute instead of 100 lines of code in an hour.
Yeah, and it's interesting because I think people may say, well, that's not correct code, but it's not that the errors are accumulating. It's just that the errors, it's a stable rate of errors, but it's changing.
Oh wow! So rate of errors and treat them as temporary blips that will get ironed out. And if you don't, if the errors do just keep on accumulating and compounding, everything falls apart. But that's not what's happening.
Yeah, if it was truly accumulated, you would see a very rapid deterioration in the system. You would not be able to write code that could even compile in your small part of the code base, right? And so it's interesting because that seems like a worthwhile trade-off, because you could add another system to this where you just occasionally take checkpoints as code, and then you have an AI agent do kind of a final quick fix-up of the small bugs, and so you have a working system that is
catching the gold and catching a release.
Exactly.
Exactly. Yeah. And so FastRender itself, it seems to me that it's not really destined to become a Chrome competitor, but it is the perfect research project for trying out large-scale coordination things against.
Definitely, I think from the beginning it was a kind of a research experiment. The output of this kind of experiment, we never intended for it to be kind of a production software or usable, but we wanted to observe behaviors of this harness of multiple agents, see how well they could work at scale. Yeah,
it's hard to imagine that ever at what point in 10 years time it could still be a completely valid research target for trying out the latest generation of agents against. It's the
I agree.
I mean, I guess it's like if you saturate your benchmark, right? If you ever evolve it to the point where it's a perfect browser against all websites, it loses its value, because now you need to find a new project to maybe put up a new Linux kernel or something.
Yes, it's in some sense, I think it's a really good kind of target project, not only because it's complex, but they have these specs. It's a kind of a usable thing if it works. You can kind of see it working, and there's a thing there. But there's also a very, very long tail of things you can do, right? And it's interesting to see how far can it get in that long tail.
Just performance optimization, right?
Exactly.
And the only job is to make this thing faster. That's fascinating, and you can learn a ton from watching them do that.
That's great. That's a great point. One of the most interesting things we learned was that you kind of you should explicitly instruct these things to treat the code as kind of perhaps pathological or uncertain, or could do anything arbitrary, right? So you should have very tight memory bounds and timeouts around when you run this code, because it could be in an unstable state that a normal engineer may not need, because they can just kind of see it running kind of weirdly and stop and iterate. But agents may just keep running it, and also that if you have aggressive timeouts forced on these, in some sense they're actually forced to optimize code as they work, right? So because they cannot actually get it working, and if they don't have it able to run under the time limit. That was another kind of interesting emergent behavior.
So I feel like we should wrap things up, but as a closing question, what are some of the most surprising things that you learned on this project? The things that really did, what are some good sort of closing ideas to give people that are things you picked up on this that surprised you along the way?
I definitely think the biggest thing, I think it's the main thing, which is I think these agents are surprisingly capable at this point. We're talking about agents that run for hours and hours, single agents, and are able to kind of hold the context, keep on the right direction, and actually know when to stop, when it's actually finished. and work within a very large code base that it has to kind of do kind of surgical or specific tasks, and not just like deliver a big feature on its own.
Isn't it fascinating how GPT 5.2 is a 400,000 token context window? Claude Opus only has 200,000 tokens. And there was this assumption previously that if the code base doesn't fit in the context window, it can't do the work. You've got way more than 400,000 tokens of context going on. And yeah, like you said, they can do surgery. They can read just the little bits that they need for their problem and get things done that way. Yeah.
That's right. Yeah, I think the interesting thing now is long-running agents are possible through context management that are quite simple, like just using a scratchpad, for example, and a loop, that kind of continuation loop where we continuously nudge the agents to keep working. Simple ideas can extend these agents well beyond a single context and run for many hours, thousands of turns.
And are your agents doing the to-do list trick? Because I found certainly with Claude Code, that seems to work really well. It spins up a bunch of to-dos and works through them one after another.
No, we use a scratchpad, and it's just a regular file, and we're not very prescriptive about how we should use it, other than that it should frequently use it and update it. And that's kind of main context management storage.
The role of the to-do list is actually your planners, right? Your tree of planners is the thing that's serving that same purpose as my to-do list and Claude might do.
Yes, that's right. And I think to-dos are also perhaps in some ways helpful for the user to see what's going on, but in such autonomous systems where the user is not sitting there all the time observing, perhaps a scratchpad is a more direct approach to context. Yeah.
Well, thank you so much for your time. This has been Wilson Lin from Cursor, talking through the fact that you can run between 2 and 20,000 agents at once and actually get a working project out of them. This is such a fascinating conversation. And I think I speak for everyone. We'd love to know more. The more that you can share about the inside details of the system, the better, because this has been absolutely fascinating.
Definitely, for sure. We'll have follow-up write-ups and technical deep dives very soon. So
awesome. Thank you so much.
All right. Thank you, Simon. This is great chatting.